Hi everyone, this video is the solution to example 5 to example 8 on the topic of statically determinate frames. So this is very similar structures to the ones on the previous video. So we could see straight away this load of 30 in this cantilever framed. It will make our bar CB bend towards the right a little bit. Then this angle here is the same angle as it is originally, so that's the same size, and then the loads of 30 will bend our bar down a little bit, so it should get more or less this type of deformation. What's important is to understand we have tension on the top and tension on the left, so we know when we do our bending moment diagram that that's where we need to draw the diagram. So in this particular case, we know the moment at A is 0, we know the moment at B should be 30 times 4, so that's 120, and since we know that we get tension on the top, we should get our moment like this. The moment transfers outside, so the moment now in this case here is also 120. And if we try to think about the moment at C, that should also be 120. So that's the bending moment diagram. Okay? In terms of shear force, we can see that this bar is actually 5 meters long. So the slope here is not 30, is 120 divided by 5, which is equal to 24. So what's going on here in terms of shear force diagram? We know that since our moments are constant in the column, we know that the shear force has to be 0 in this case, which makes sense since we know the reaction here at C, the horizontal, is equal not to 10, but it's equal to 0. The vertical reaction is indeed equal to 30. So why are we getting that the shear force in this bar is equal to 24 and not 30? And that's because the load of 30 is not perpendicular to the bar AB. So with a little bit of trigonometry, you can see that the component in that direction of the load 30 is actually 30 times 4 over 5, so it's the cosine of that angle, and that gives you the 24 that we're looking for, okay? So that concludes the diagram on this case. We can then move on to the next one. So very similar deformation, we can get something that will look like that as well. So we can draw straight away our bending moment diagram, trying to say that the moment at A is 0, then the moment here is equal to 10 times 3 clockwise plus 20 times 4, so that's 80 plus 30 is 110, and that just transfers there, and this again transfers outside, so that's 110. And now, do we have more moment at C? Yes, we do. So it's 20 times 4, 80, plus 10 times 6, 60. So we're going to get a moment here of 140. Okay? This means that the slope here is going to be 10, right? It's 30 divided by 3. So the slope here is 10, which matches very well with this horizontal reaction that then will do the shear force in CB. The slope in this one is the same as the previous case, is 110 divided by 5, which should give you 22. So then we know the 22 is the shear force in that bar. Now, the value of that 22 is again obtained using a little bit of trigonometry. But before we get there, we can say that the shear force diagram will be with a 10 on this bar here, and then we know it's 22 on this one. So where is the 22 coming from? Is again the component of this 10 and this 20, right? We have this 20 acting there and we have this 10 acting there, and we're trying to figure out what are the components of these two forces perpendicular to the bar. And if you guys do it with a little bit of trigonometry, you can find out that the value is 22. Okay, so we can move on into the next problem. So in this problem here, if you try to draw the deflection, you'll see that it's not straightforward. You could try to guess that your deflection could very well maybe look like that or something. But here you can see we're breaking the rule here. This needs to stay a 90-degree angle. So it's not straightforward to start with a deflection in this problem. So if this is not easy for you, that's no problem. You can start with the bending moment diagram, or you can start with the reactions. So let's say, for example, the reactions. We know here the horizontal is 0, the vertical is 30, And then in terms of moment, we have a clockwise of 30 times 4, so we know this moment here is 120. So now, when we go to the bending moment diagram, we can start thinking about this all together. So we have 120 here that will cause the bar to have tension on the left side. That's the value here of 120. And since we don't have shear force, we know that this here is 120 constant all the way to the top. Then that 120 transfers outside, that's the value over there. And now we do have a load of 30, that's our shear force. So the load of 30, shear force of 120, and we also know the moment at A is 0, but very important as well, the moment at B also has to be 0 because we don't have a distance from the load of 30 to the point B. So here, this just connects down, and here is our slope of 30 that we just thought about as the shear force of our bar. So this is the bending moment diagram. And in this case, for the deflected shape, what we know is that this point here needs to stay flat and without displacement, but then our bar will start having tension on the left side. Here I want to maintain my 90-degree angle, so my bar will have tension on the top. And then finally, since we know the last bar doesn't have bending, and we need to keep our 90-degree angle there, we can just draw our deflection here. And pay attention here that this has no bending. Okay? So this is my guess for the deflected shape in this problem based on the bending moment diagram and what the structure looks like. Okay, now let's look into the last problem. Here, same logic. Maybe the deflected shape is not the best place to start. So let's maybe start with the bending moment diagram and the reactions, so then we can then do the deflected shape at the end. So we know we have 30 to the right, that means our reaction is 30, then is 0, and then we have a counterclockwise moment of 30 times 3, so then we need a clockwise reaction of 30 times 3, which is 90. So straight away we can see that this will cause tension on the right side, the moment of 90. So I'm going to draw it here. But now the load of 30 is a shear force, right? So we have a shear force of 30 in this bar. Okay, so with this information, I would say we can start understanding that the moment will go in this direction. But okay, let's think about it from the other angle now. We know that at A, my moment is 0, and then I have a load of 30 that is pushing bar A, point A to the left, so that means this should bend more or less in that direction. So I would say the moment at B should be equal to 90, like that. And again, tension on the right side. Then this transfers outside, so that's my 90 going over there, and this is my 90 here, constant, because the moment here is also 90, but the moment there is also 90. And you guys can see that when I push this point inwards, most likely this will bend like that, and then with the 90 degrees, this will do something like that. So we have tension on the top, this is all adding up. Then we have here our 90, transferring outside, and now we're in a situation that we can connect these 2 points like this. Okay, so now I'm happy with the bending moment diagram. What we can do next is with this, think about the deflected shape. And here we can start understanding that our bar first bends towards the left, so tension on the right side. But then when it gets towards the middle, we stop having bending just for a little bit, and we start having tension on the left side. Now, probably this doesn't turn as much as I just draw here. This will still have an angle when we get to that spot, because it's this angle here that will give me my 90-degree angle. So then I can have my tension on the top side, and this will close like that. And then finally, 90-degree angle here, and this bar will bend inwards. So under a loading scenario like this, with a load of 30 there, I think this deflected shape makes some sense. So here bends towards the left, then it starts bending towards the right, here bends on top, and then here bends on the right side. Okay, so that's the solution to these problems. If you want to think about shear force diagram, you can think about it. Here the slope is 30, here the slope is 0. so we shouldn't get shear force, which makes sense with this load here of 0, and the slope in this case here is also 30. Okay, so thank you for watching these problems. We have 2 more videos on this topic, now talking about simply supported beams. Hope this made sense, and have a great day.